This is the sixth video on section 6.6, Lagrange multipliers. And in this video we're going to use the previous Lagrange theorem to solve example 196. So we have f of x, y, z is 2x plus y squared minus z. And we want to optimize this function subject to two constraints. The first one being x squared plus y squared is equal to 1. And the second one being x plus z is equal to 4. This is a cylinder in R3, right? So we have x squared plus y squared is equal to 1. This is a cylinder, and this is a plane. So we're looking at the place where the plane cuts through the cylinder. Remember, a continuous function on a closed bounded region has a max and it has a min. Polynomials are continuous functions. The place where the plane slices through the cylinder is a closed bounded region. So we have a max and we have a min. We're going to use Lagrange's theorem to find those. So remember, we want the constraint g equal to 0, so we simply have g x y z as x squared plus y squared minus 1. We also want to look at the constraint h equal to 0, so we set h of x y z equal to x plus z minus 4. Now we look at the equation. Gradient of f is equal to lambda times the gradient of g plus mu times the gradient of h. Remember, we're looking for two Lagrange multipliers this time, lambda and mu. So we calculate the gradients and we have this vector equation. So now let's look at the components to see what we can figure out about x, y, z, lambda, and mu. So we have these three equations from the components. So we look at the first components, the second component, and the third component, and we got these three equations. From the first component, we see that 2 lambda x plus mu is equal to 2. So 2 lambda x plus mu is equal to 2. From the second component, we have 2 lambda y plus 0 is 2y. So we have 2 lambda y is equal to 2y. From the third component, we see that 0 plus mu is negative 1. And so mu is equal to negative 1. So we have our three equations. Let's look at the second one. So we look at the second equation, 2 lambda y is equal to 2y. So lambda y is equal to y. That tells us that either y is equal to 0 or lambda is equal to 1. So let's explore those. If y is equal to 0, go back to this constraint right here. If y is equal to 0, then x is either equal to 1 or negative 1. If x is equal to 1, then z is equal to 3. If x is equal to negative 1, then z is equal to 5. And so y equal to 0 gives us 2 points to look at. One of those points is 1, 0, 3, whose function value is negative 1. The other point is negative 1, 0, 5, whose function value is negative 7. So we hang on to these. This could be the max, and this could be the min. So we're going to explore this further. So that's what happened if y is 0. But what if it's not? So remember, this means y is 0 or lambda is equal to 1. So what if lambda is equal to 1? We look at this first equation. 2 lambda x plus mu is equal to 2. Lambda is equal to 1. So we have 2x plus mu is equal to 2. But remember, mu is negative 1. So that means 2x is equal to 3. And so x is 3 halves. However, look at our first constraint. X squared plus y squared is equal to 1. This is not possible. If x is 3 halves, x squared is 9 fourths. 9 fourths plus y squared cannot be 1. Okay? It doesn't matter what y is. If x is 3 halves, then x squared is 9 fourths. 9 fourths plus a non-negative number cannot possibly equal 1. So this is not possible. So that brings us back to our two things that were possible up here. So our min is f of 1, 0, 3, which is negative 1, and our max is f of negative 1. I had that backwards, I'm sorry. The max is f of 103, which is negative 1, and the min is f of negative 105, which is negative 7.